Okay, so as we look at this problem, we draw our free body diagram. So here's our system. What all forces are acting on this system? We have gravity. And what other force counteracts gravity in this case? The normal force. Tell me why it's the normal force. Because it's resting on a surface, okay? It's normal force when it's resting on a surface. Okay, what about this forward force here? We assume that it's going to be going in the positive direction, okay? So we're going to say this is going right here, and we'll just call it force forward. You could call it an applied force. You can call it whatever you want, okay? You don't have to label them exactly how I do. So that's our forward force. Tell me overall what this question is asking us for. Time. Okay, time is going to be our overall goal here. How can we get there? How do we have to get there to find time? What's our first step? We have to find acceleration. Okay, so in our problem, we can take away that we have our overall net force. Okay, how do we know it's our overall net force? We're going to look at whether we're dealing with horizontal or vertical components here. What do you think? Horizontal. That means we don't care about this normal force. We don't care about the gravitational force because we're only looking at horizontal motion. Okay, so the net force is the sum of all of our forces. The net force is always going to be right minus left or up minus down. Okay, so since we are using horizontal forces, we're going to take our rightward forces and we're going to subtract out our leftward forces. So our rightward forces are force of forward or force applied or whatever you chose to name this force as right here, minus any forces that we have to the left. Do we have anything that's going left? No. So you can write minus 0 if you'd like. You can leave it blank, however you'd like. Okay? Since we know that the net force is the sum of all of our forces and we only have one horizontal force, that's it. Okay? That's what the net force equals. Okay? And it tells us that this forward force is 3,500 newtons. So we plug that in right here. Okay, we can do a substitution for our net force here. What does net force also equal? Mass times acceleration. Okay, are we seeing where these numbers are coming from thus far? Give me like a head nod if you think yes. Okay. So we know the mass, it's given to us right here. So 1,200 A equals... Okay, now we're ready to move on to the second one. How many people totally understand how to do tension problems? Nah. Okay, so we're going to start from the beginning. Start totally from the beginning. All right, so let's draw out what the system looks like. Okay, the system itself. A crane operates is a 1,550 kilogram ball attached to a 1,400 kilogram ball with an upward acceleration of 2 meters per second squared. Find the tension in each cable, assuming cables are massless. Okay, so the top one is the 1,550. The bottom one's the 1,400. So this picture makes sense to everyone, right? This is what the problem is setting up as. Okay, so the tension, we need to find the tension in each cable. So this cable here, we're going to call force of tension 1. This cable here, we're going to call force of tension 2. Okay, this is how I would set the problem up. So we're going to look to find the tension in each of those cables. So we're going to start with finding the top one first. So we're going to find this cable first. This is what the free body diagram looks like for this top system. Okay, we divide these kind of in two systems. So this top cable, we're going to draw the free body diagram for it. So what's that force is acting on this top cable or this top of the system? What are we looking at here? There's tension that's pulling up on it. And what's pulling down? Force of gravity. Okay? So here, right now, we're looking at this cable right here. So we're looking at the whole system below it. Everything below it. Okay? Does that part make sense? For this top cable, we have to look at everything hanging below it. Okay, great. So then we go to write our net equation here. Our net force is the sum of all forces acting on this object. And we take up minus down. So we're going to take our force of tension 1 minus F sub g. Okay, this equation right here, very important. Okay, it's very, very important for us to write this equation. Does this part right here make sense? Yes. How we got this? Top minus bottom. Okay, great. So now, once this equation is written, then we can do our substitutions. So F net also equals what? Mass times acceleration. We want to solve for F sub T1, so we don't substitute anything in for that. And we know what Fg equals. What's that? Mass times gravity. Very good. Okay. So since we're looking at this whole system right here, what's the mass have to be? Exactly. Those two added together. So 1550 plus 1400 needs to go in for our mass. So I'm just going to add that. 2950 for our mass. And what's the acceleration of the whole system? 2. Okay, that we found that from right here. Is it positive 2 or negative 2? Positive, exactly. Positive because it's accelerating upward. So we just plug in a 2 right there. We want to solve for our tension force. And then we subtract out the mass again, 2950 times gravity, which is 9.8. So from here, simple algebra. Okay, do the math, subtract it over, you find force of tension 1. What did we get for our force of tension in the top cable? 34,810. And what unit do we need to use for this? Newtons. Why do we use newtons as our unit? Exactly, because we're solving for a force. So whenever we need to solve for a force of something, our units has to be newtons. Okay, how do you feel about that? Better? Okay. Alright, so we have the tension in our top cable. Now we need to solve for the tension in the bottom cable. So I'm going to erase this work. What is different about the top cable and the bottom cable? Yeah, just the mass. Does the free body diagram look the same? Yeah, so I'm just going to change these F sub T1s to F sub T2, okay, rather than erase the whole thing, okay? For the bottom half, we're only looking at, this bottom cable, we're only looking at this system in red, okay? So that's the only section of this that we're looking at. So our free body diagram stays the same, except we add an FT2 right here instead of FT1. And we solve it exactly the same way. So our mass then is only 1400. We take that times the acceleration. The acceleration of the whole system is the same. It does not change. We solve for F sub T2. And we do the math and add it over. All right, what did we get for the answer of our tension in the second cable? What did you get? 16,520. Is that what everybody got? And what should our units be? Okay, that's it. Okay, so for the elevator problem, our free body diagram looks like this. We have what pulling down on him? Gravity, always force of gravity pulling down. And what's pushing back up? The normal. Okay, when he's sitting on the scale, gravity's pulling him down, the scale is pushing him back up. Okay, so that normal force is what we want to solve for. That's what the scale will exert back up. Okay, that's what the scale would read. So you could also label this F of scale if you wanted to. If you so choose, you could do that. But this is what we're solving for. Okay, so our net force equation will look like what? F net equals what? Exactly. Fn minus Fg. Then after this equation is written, we can do our substitutions. So F net also equals mass times acceleration. We're going to solve for the normal force so we don't change that. Fg is also equal to mg. Very good. So now we plug in numbers. This is one, Madeline, where it says it's accelerating downward at a rate of 4.5. So our mass is 40. Our acceleration is then what? Negative 4.5. We're solving for the normal force. We want to take mass times 9.8, which is force of gravity. And we solve for F sub n. That's it. All right, so what did you get for the normal force? Okay, Claire says 212. Great. What should our units be? Newtons. Very good. Okay, this problem says we're looking to find what? Horizontal acceleration, okay? So let's go ahead and draw our free body diagram, and then we'll see why that horizontal acceleration is important. Okay, so free body diagram, what forces are acting on this box? Normal force, because it's on a surface. Force of gravity. And what other force? The applied force, right? Because she's dragging this crate with some force. Okay, so this applied force, can we work with forces that are at angles like this? No. We need to find components of that force. So this will be our force applied in what direction? Y. And this will be our force applied in the X. So here's what our force diagram looks like. If we want to redraw, we can add these on to the real free body diagram. It's up to you if you choose to do that. But let's take a look at what the problem is actually asking. Okay, it's actually asking for horizontal acceleration. That means what type of forces are we going to be really concerned with? Just the X, just the horizontal ones. Okay, we're looking for horizontal acceleration. That means we don't care about these vertical ones at all. We don't care. Okay? So that means when we write our net force equation, what are our right forces minus our left forces? What's our right force? Yes, F applied in the X direction. Do we have any forces that are going to the left that we need to subtract out? No, because it says ignore friction. Okay, so you could put a minus 0 there if you'd like. I usually don't. So what else does the problem tell us? What else do we know? What can we do next? Yeah, we have to find the angle. We have to find this force applied X. Because we have our total applied force. We have the angle at which it was applied. So we need to find this right here. Our force applied in the X direction. And what trig function do we use? Cosine. Very good. So it's 30 cosine 20, and we get, I think, 28.2. So 28.2 is our force applied X. So all we do is plug it in up here, 28.2. Okay, then we can do a substitution. What do we know force net equals? Mass times acceleration. We know from the problem that the mass is 16. So we do 16a equals 28.2. And then we know our acceleration is equal to what? 1.76. What units do we use for acceleration? Let's draw the free body diagram for this problem. Okay, the box sitting on the floor. There's an applied force. We assume that goes in the positive direction. So we'll just call this force applied. What other forces do we have horizontal? Friction. Okay, then what vertical forces do we have? Good. Normal force and gravitational force. Why? Oh, okay. I don't know why I did that. Sorry. Okay, so let's think about what's happening to the present. Is it moving vertically at all? No. So we understand that it's not moving vertically. What does that mean when the normal force and the gravitational force?
They're equal.
They're equal. Okay, tell me why they're equal, Tommy.
It's like it's not moving.
Yeah, it's not moving. It's sitting still. When the net vertical force is 0, that means those two forces have to equal out. Okay, so these two, F sub G and F sub N, should be drawn proportionally equal. So, part A, what's it asking for here? Part A. Force due to gravity, which is F sub G. We know F sub G equals what? Mass times gravity. That's it. That's all that question is asking for. Okay, so the mass is 25. Gravity is 9.8. We know it's what? 245. And what units? Newtons. Okay, and we might also put like a little down arrow because we know that gravity's pulling it down. Force of gravity's pulling it down. So if we know that the normal force and the gravitational force are equal, what do we need to do for part B? Just write the answer. That's it. Okay, 245. And we can say up if we wanted to. Okay, I'm not going to count off if you don't have that. But just so you know, you could do that. Are we good to this point? Let's look at what part C is asking us. We want to look for horizontal acceleration. That means what forces are we dealing with? Friction and applied. So our net force equation here will be what? Force what? Exactly. Applied minus force of friction. Luckily, those two numbers are given to us in our problem. So the net force equals 110 minus 80.85. So that makes our net force equal what? 29.15. Then we do our substitution and we see mass times acceleration equals 29.15. And then we can plug in our... Sorry, I have to move up because I'm running out of room. We divide by 25, we divide by 25. And our acceleration is what? 1.17? Okay, since we're solving for acceleration, that means our units are meters per second squared. Okay, so draw the free body diagram of a box sliding across the floor at constant velocity. What do we know the net force is of something at constant velocity? 0. Okay, so that should have been your first move. Mark a 0. Some people tried to attach numbers to this problem. Not necessary. Okay, I just needed the free body diagram. I think some of you might have been confused if it was attached to the one above that. It's not. Okay. Okay, so separate. So let's draw the free body diagram here of our box. If it's sliding across the floor, that means it has to have some sort of applied force that causes that slide. So we'll just say this is our applied force. It tells us to include friction. So how proportionally should the friction be compared to the applied force?
Smaller.
Why smaller? No. It's moving at constant velocity, so those net force has to be 0, so they need to be equal. They need to be drawn of equal lengths if it's moving at constant velocity.
Then how would it be sliding?
Okay, so what vertical forces act on this box? And what's our up force? Normal, because it's resting on something. It's on the floor. So that's it. So I want to point out this. When something is at constant velocity, we know the forces have to be equal. But does the applied force in this case, or this force right here, have to equal the gravitational force? No. No. When something's at constant velocity, the horizontal forces have to equal each other, and the vertical forces have to equal each other. But horizontal does not have to equal vertical.